Welcome to our Physics 135A tutorial video. So this is Introduction to Vectors, Displacement, and Velocity. We've completed this in class. We're just documenting here the solutions. So as we saw in class, we have a two-dimensional coordinate system, and the unit of the coordinate system that's appropriate is in kilometers. The initial position of the submarine that's being chased by a torpedo is here. It's a kilometer back from the origin, and the torpedo is 2 kilometers back. So the initial position of the torpedo is -2 kilometers, whereas the initial position of the submarine is 1 kilometer back. And those are positions relative to the origin, and both systems, the torpedo and the sub, are going to arrive right here at the canyon wall, which is to the right of the origin. If we zoom in on this triangle, this is actually a 45 degree, 90 degree right triangle. And we're told in the figure subcaption that this length here is 1/2 of a kilometer, but if it's a 45, 90 degree right triangle, that means that this is also 1/2 of a kilometer. So the location of the canyon wall to the right of the origin, this point, is 1/2, 0 kilometers. So those are the coordinate pair, or you could say, the position of the wall, for example, would be 1/2 I plus 0 j in kilometers. So that'd be another way of writing it. So the question is, first, write down the displacement of the submarine from the initial position as it reaches the canyon wall, and the displacement of the torpedo as it reaches the canyon wall. What is displacement? The difference between the final and initial positions. So the final position for both this torpedo and the submarine is going to be 1/2 in the x direction and then 0 in the y direction, but they have different initial positions. So let's do the example of the submarine. The initial position of the submarine is -1 I plus 0 j, and those are in kilometers. And so the displacement of the sub will be the final position, that is 1/2 I plus 0 j. That's the final position here, minus the initial position, which is 1 kilometer back from the origin. And so you can kind of tell intuitively that if it starts here and goes a kilometer and then another 1/2 a kilometer, it should be 1.5 somehow. And you see that it is. These are both zeros, so they don't enter into the final answer. You have a 1/2 minus -1, so we have 1.5 kilometers, but in the positive x direction. So here I would say 1.5 kilometers to the right, and specifying both the magnitude and the direction is perfectly acceptable. So what about the torpedo? Well, by the same logic, the torpedo, although it starts from a different place, it winds up here, so that's the final position of the torpedo. The initial position of the torpedo is -2 I plus 0 j, and those units are in kilometers. So by the same logic, we do the subtraction and we get 2.5 kilometers to the right. How do we get that? Well, the final position is, again, 1/2 I plus 0 j minus -2 I plus 0 j, and everything's in kilometers. That's the relevant unit. And so here we have minus -2, so it's 2.5, 2.5 kilometers to the right. So velocity is simply the ratio of displacement to time duration. Time duration is defined just like displacement, where it's a final quantity minus an initial quantity, except time is not a vector. If I multiply both sides by delta t, then you get delta x is equal to v delta t, or v is a velocity vector. And then you can take the absolute value of both sides. If you're not so concerned at the moment with the direction, you can just write these as scalar numbers. Delta x is equal to v delta t. And that will suffice for calculating speeds and times given velocities. Well, what's the question here? Assume the situation begins with time initial of t equals 0, so delta t will be t final minus t initial, or 0. So determine when the torpedo hits the canyon wall. So we're being asked when. That's the key word right there, when. And I'm saying specifically what's t final. But I circle that heavily because that when word is everything, right? It tells you what you're being asked. The quantity specifically is the time duration that it takes a torpedo to travel from its initial position to the canyon wall. So we're going to solve this formula for time duration. That's delta x over velocity. But delta t is t final minus 0 in this case because t initial happens to be 0. So delta t is equal to t final. So t final is delta x divided by v. What is delta x for the torpedo? We just found that it was 2.5 kilometers no matter what direction it's going. It went 2.5 kilometers. So 2.5 kilometers divided by the torpedo is moving at 50 kilometers per hour. It says that back on the first page right here. The initial velocity of the torpedo is 50 in the x direction. What are the units? Kilometers per hour. So if we know that 50 kilometers per hour, let's handle those units first. The kilometers cancel. 1 over 1 over 1 hour is just an hour. And then what's 2.5 over 50? That's like saying 1 over 10, 25 over 50. That's a half. So this is 1 over 10 times 2, which is a 20th of an hour, and that happens to be 3 minutes, if you convert that to minutes. So a 20th of an hour, or 3 minutes. And so what I want is for the submarine to also have that same time duration and whatever the displacement of the sub is, happens to be 1.5 kilometers from its initial position to the canyon wall. And so our Vx, which is just the displacement over the time change, is 1.5 kilometers divided by 3 minutes. So half kilometer per minute, but let's get this into maybe kilometers per hour. So if we have 60 minutes per hour, minutes cancel, we're left with kilometers per hour. And so we have 1.5 times 60, that's 90 over 3, which is 30 kilometers per hour. So Vx, 30 kilometers per hour, and the point I'm making here is that according to the strategy of the situation, the captain chooses a speed which is deliberately slower than the torpedo, or I mean, could he go faster? Yes, but he decides to go at that speed so that the torpedo appears to have destroyed his ship, but instead it hasn't, and they escape, and their attackers think that they are dead. Captain Ramius continues at the same speed, but the boat turns at an angle of negative 45 degrees with respect to the x-axis. That's shown here. So this is the second leg of the journey. The sub goes that way. After 3 minutes, what is the final location of the sub? Well, let's consider the first. We'll model the triangle here. So the hypotenuse of that triangle will be the vector. And then at the same speed, 30 kilometers per hour for another 3 minutes, that's another 1.5 kilometers, but now it's down and to the right. And so if the hypotenuse is 1.5 kilometers, and we know this is a 45, 45 right, 9-degree right triangle, then we have 1.5 over square root of 2 for the side lengths of this triangle. So from here to here, the displacement would be positive 1.5 over root 2 kilometers to the right, and then that same number but down. But remember, we're not proceeding from the origin. There's another half a kilometer here. You see that's half a kilometer to the right of the origin where the tip of that triangle is. So this tip right here is not the origin. That is a point which is half a kilometer to the right of the origin, and then no kilometers up or down. So the final location will be, like if this is the origin, it's half a kilometer to the right, another 1.5 kilometers divided by the square root of 2 to the right. So if I say x final for the submarine, I have to say the half a kilometer plus 1.5 over root 2 in the I direction, and then the only change in the y direction is this one, the down portion of the second leg of the journey. So that's negative 1.5 over square root of 2j, like that. So those are the vector components of the final position of the submarine. What's the displacement of the submarine? So initial position of the sub, x initial, that is from the beginning of the problem, was negative 1i plus 0j, and then now we have x final for the sub, which is 1/2 plus 1.5 over root 2 I, and then negative 1.5 over the square root of 2j. And all those distances are in kilometers. So the displacement will then be the subtraction of x final minus x initial. Notice if you subtract x initial, the only term is really this negative 1i, and then the units are kilometers. So if you subtract minus 1, you get the following: 1/2 plus 1.5 over root 2i, and then minus 1.5 over the square root of 2j. That's the x final. But I'm going to subtract the minus 1i plus 0j, and so this becomes just a positive. And so the displacement of the submarine is 1.5 plus 1.5 over root 2. And then negative 1.5 over root 2j. So what are those numbers in terms of decimal points? So 1.5 plus 1.5 divided by the square root of 2 is 2.56, and then 1.5 divided by the square root of 2 is 1.06. So the displacement here is about 2.56 kilometers to the right, and then minus 1.06 kilometers down. The final question here, though, is asking about what is the average velocity. Well, to get the average velocity, you just take the displacement and divide by the time duration. But the time duration here is 6 minutes. 3 minutes for the second leg of the trip, and then 3 minutes for the first leg of the trip. So 3 minutes here, and then another 3 minutes. And so 6 minutes is a tenth of an hour. And so our delta t then is 0.1 hours. So I'm going to do some erasing to create some room. But I'm going to save that final displacement value there. And then I've got delta t. So I'm going to take the ratio of these two things. The velocity is delta x divided by delta t. Now when you divide anything by 0.1, it's like multiplying by 10. So that's multiplying by 10 is 25.6 I, and then minus 10.6 J, and then I've divided by an hour, actually a tenth of an hour, but I've divided by the units of hours, so it's kilometers per hour. This is the average velocity, this is the displacement.